Okay, so let's recall, first of all, the dot product. So if we have two vectors, u and v, in three-dimensional space or two-dimensional space, the dot product is the length of u times the length of v times the cosine of the angle between them. And because the cosine is an even function, cosine theta equals cosine minus theta, it doesn't matter whether you take the angle going in the positive direction or in the negative direction, it's the same cosine. And if u has coordinates u1, u2, u3, and v has coordinates v1, v2, v3, then the dot product is simply the sum of the products of the first, second, and third coordinates. And one of the most important properties of the dot product is that it enables you have a vector u and a vector v to find the projection of v in the direction of u. So if you take the vector v, you might want to compose it for various reasons. One does this a lot in physics. As the sum of a vector parallel to u and a vector perpendicular to u. The component parallel to u is called the projection of v in the direction of u. And this is the dot product of u and v divided by the length of v squared, or the dot product of v with v. This is a scalar times u. So this is a scalar, a number, and this is the vector u, right? And recall, for any vector u, or any vector, should be a u here, the length of u is the square root of the sum of the squares of the coordinates. So the length of u squared is u1 squared plus u2 is the sum of the squares of the coordinates. You square the square root, you get u1 squared plus u2 squared plus u3 squared, which is exactly the dot product of u with u. So you could also write dot product of u with u in the denominator. So this is the dot product. And one thing to keep in mind is that the dot product of two vectors is a number, is a scalar. And sometimes the dot product is called the scalar product. Now, this makes sense in 2 or 3 dimensions. So u and v can be vectors in R2 or in R3. If the vectors in R2, it's the same formula, except u3 and v3 are 0. But there's another multiplication of vectors whose product is a vector, and that's called the cross product. And that only makes sense for vectors in 3-dimensional space. It's only defined for vectors in 3-dimensional space. So we can talk about the cross product of vectors u and v in R3. Again, not R2. We never talk about the cross product of two vectors in R2. And this is going to be a vector. And to understand that vector, we define this cross product, u cross v, as follows. So a vector has a length and a direction. So the magnitude of the vector, the length, which we always know by these vertical lines, absolute values lines, the length of the vector is the length of u times the length of v times the sine of the angle between them. And we take the angle theta as going from u to v. That's my angle theta. And the sine can be positive or negative. But if we take the sign to be the angle always between 0 and pi, this is positive. So this is always going to be greater than or equal to 0. And the only time, so if u is not the 0 vector and v is not the 0 vector, then the length of u is positive and the length of v is positive. And so this cross product of u times v, the only vector that has 0 length is the 0 vector. So the only time this is going to be 0 is if the sine of theta is 0, which only happens when theta is a right angle, pi over 2 radians. So, sorry. This is all completely wrong. If and only if sine of theta is 0 or pi. So it's only parallel vectors that have 0 cross product. But what about the direction? The direction of the cross product is determined by the right-hand rule. Namely, you take the vector u, place your hand, imagine placing your hand, so the vector u, so the heel of your hand is at the intersection of these, at the origin. If you rotate u into v, your thumb is pointing in the direction of the cross product. So let me just switch for a second to sharing the screen with the text. So you should see this picture on your screen, and this is the picture of the right-hand rule. Here's the vector u. Here is the vector v. You place the heel of your right hand at the origin. Your fingers point in the direction of u, and you rotate them in the direction to v through this angle between 0 and pi. And then your thumb is pointing in the direction of the cross product. All right. And just as with the dot product, remember, the dot product was defined geometrically. This was the original formula. The length of u times the length of v times the cosine of the angle between the two vectors. We defined, but then we showed that the dot product can also be defined in terms of the coordinates of the two vectors. So we started with this as a definition, and we proved this. So I want to do the same thing with the cross product. This is the definition of the length of the two vectors, and the right-hand rule gives the direction of the vectors. But I would like to find the coordinates. I would like to find the cross product u times v in terms of the coordinates of u and v. So that's our immediate goal. Maybe I'll try to do one example. This is an example which is the first example in this section in the text. Suppose u is the vector 1, 1, 0, and v is the vector 1, 1 square root of 2. So I am very bad at drawing pictures. But if this is the x, y, and z, these are the x, y, and z axes, the point 1, 1, 0 is here. And if we go up, square root of 2, this is square root of 2 in the z direction. This point directly over this point in the xy plane, this is the point 1, 1, square root of 2. So we have this vector in the xy plane and this vector in 3 space. What is the length of u? The length of u is the square root of 1 squared plus 1 squared plus 0 squared, which is the square root of 2. The length of v is the square root of 1 squared plus 1 squared plus root 2 squared. That's 1 plus 1 plus 2 is 4, is 2. So you can't see it very well from this picture, but this vector has length 1. So this is my u, and this is my vector v, and this vector going up into space has length 2. And what is this angle between them? Theta. So if we look at this vector is directly above this one. So this would be a right angle. So it looks like we have a picture like this. So this is going to u, this is going to v, this length is 2, this length is 1. That means this length is the square root of 3. So you know that this is pi over 2, and this is pi over 3. So the angle from u to v is pi over 3. So in this picture, theta is pi over 3, and the sine of pi over 3 is root 3 over 2. Let's see. Let me just go through this again. This is 1, 1, 0. This is 1, 1, square root of 2. So in this triangle, this height is square root of 2. And this is 1. That means this also has to be 1. Sorry. This is square root of 2. Yes. This is square root of 2. This is square root of 2. So this is actually isosceles right triangle. And this is 2. So this angle is pi over 4. Sine of pi over 4 is 1 over root 2. So let me draw this again so there's a better picture. So here is my vector u, which is 1, 1, 0. And above it is the vector v, which is 1, 1, square root of 2. So this is directly above this. This height is the square root of 2. And this length is the square root of 2. So what we really have is a right triangle, square root of 2, square root of 2, which is isosceles, root 2, and this distance we saw is 2. So this is u, this is v, and my angle theta is pi over 4. So for the cross product, the magnitude of the cross product is the length of u, the length of v, times the sine of the angle between them. The length of u is root 2. The length of v is 2, and the sine of pi over 4 is 1 over root 2. So u cross v has length 2. And what is the direction of u cross v? Well, if you take this vector and you rotate it using your right hand, u into v, there's no way for me to draw this, but it's something which is pointing. So if you look at the plane formed by these two vectors, it is perpendicular to this plane and in this direction. And I notice even the book can't draw this very well. Let's just look at the picture in the text for a second. So this is the picture of this exercise, of this example. U is the vector 1, 1, 0. Above it, in 3 space, is the vector v, 1, 1, square root of 2. So this height is root 2. This vector has length root 2. V has length 2. We have this right triangle. U cross v has length 2. That's what it says right here. And the direction u cross v is given by the right-hand rule, but there's no way I can draw this, so I won't even try. There's some very nice properties of the cross product. First is that it's sort of anti-commutative. If I take u cross v, and I take the vector v cross u, the lengths of these two vectors are the same. Length of u, length of v, times the sine of the angle between them. But when you rotate u into v, you get a direction opposite to rotating v into u. So u cross v as a vector is minus the vector v cross u. So they point, they're two vectors of the same magnitude, but they point in opposite directions. So this is the first property. Second property is if you multiply u by a scalar and v by a scalar, you take this cross product, you get exactly AB times the cross product of u and v. There's a kind of distributive property. U cross product with v plus w is u cross v plus u cross w. And this is distributive in both on both sides. So u plus v cross product with w is u cross w plus v cross w. So these are sort of basic algebraic properties of the cross product. And this is all we need to be able to figure out a coordinate-wise expression for the cross product. So let's start with unit vectors in the x, y, and z directions. So we have the vector I, which is 1, 0, 0. That's in the x direction of length 1. The vector j is a unit vector in the y direction, 0, 1, 0. And the vector k is a unit vector in the z direction, 0, 0, 1. So let's compute the cross product of these vectors. First of all, each of them has length 1. If you look at I cross J, the angle between them is a right angle. So the magnitude of I cross J, length of I, length of J, sine of pi over 2, sine of pi over 2 is 1. This is 1 times 1 times 1, which is 1. Similarly, if you take J cross K, the absolute value of this is the length of J, length of K. This angle is also a right angle. And if I take K cross I, this is a right angle. So the magnitude of that cross product vector is length of K, length of I, sine pi over 2. Again, it's 1 times 1 times 1, which is 1. So the cross product of these three, any pair of these 3 unit vectors is 1. But what is the direction? If you take I and rotate it by the right-hand rule into J, your thumb is pointing in the K direction. So I cross J, it's a vector pointing in the K direction. It's of length 1. So I times J is K. If you rotate J into K, your thumb is going to point in the I direction. J cross K is equal to I. If you rotate K into I, your thumb will point in the J direction. So here we have this very fundamental fact about the cross products of these 3 unit vectors. And because the product of vectors is anti-commutative, J cross I is minus K. K cross J, if you do it in the opposite direction, is minus I. And I cross K is minus J. But these 3 equations come directly from these 3 equations. So now let's do a long calculation, but you only have to do it once, to compute the cross product of 2 vectors in terms of their coordinates. So suppose the vector u is u1, u2, u3, which I remind you is the same as u1, 0, 0, plus 0, u2, 0, plus 0, 0, u3, which is the same as u1 times the vector 1, 0, 0, u2 times the vector 0, 1, 0, and u3 times the vector 0, 0, 1. But this is I, this is J, and this is K. So u is equal to u1i plus u2j plus u3k. Okay. Any questions about that? All right. And similarly, v, it has coordinates v1, v2, v3, is v1i plus v2j plus v3k. So now let's take the cross product. What is u cross v? That's u1i plus u2j plus u3k cross, let me do it in 2 steps, several steps. So this is u times v. But then I can expand it by distributivity. This is u1 I cross v plus u2 j cross v plus u3 k cross v. But then I can write v like this. This is u1i times cross product with v1i plus v2j plus v3k plus u2j times v1i plus v2j plus v3k plus u3k cross product with v1i plus V2J plus V3K. And I continue to expand using the distributive law for the cross product. So I have U1 V1 I cross I plus U1 V2 I cross J plus U1 V3 I cross K. Here, when I expand again by distributivity, I have U2 V1 J cross I plus U2 V2 J cross J plus U3 V3 J cross K. I expand this again by the distributive law. I get U3 V1 K cross I, U3 V2 K cross J, and U3 V3 K cross K. Now, we already observed that the cross product of two vectors that are parallel is 0. In particular, if you take the cross product of a vector with itself, it's 0. So I cross I, J cross J, and K cross K, these are just the 0 vectors. That's 0, that disappears. So what do we have left? I have U1 V2 I cross J, but I times J is K. V1 U1 V3 I times K, K times I is J, so I times K is minus J. J cross I cross J is K, so J cross I is minus K. So I get minus U2 V1 times K. J cross K is I, so U3 V3 I. K times I is J, U3 V3 J. J cross K is I, so K cross J is minus I, minus U3 V2 I. So let's see, I have I occurring twice. I have this is U1 V2, U1 V3, U2 V1. This should be U2 V3. I. So I have U2 V3 minus U3 V2 I. And for J, I have what I have minus U1 V3, and here plus, which is the same as let's see, let's just double check this. This is U3 V1, U3 V1 J. So minus times minus is plus, minus U3 V1 J, and then something times K, I have minus U2 V1 plus U1 V2. And you might remember from high school algebra, if you have the ABCD, this 2x2 matrix, the determinant is AD minus BC. So this expression is exactly the determinant of the 2x2 matrix U2, U3, V2, V3. Because if you take this determinant, AD minus BC, U2V3 minus U3V2. And here we have U1, U3, V1, V3, that determinant times J. And here we have this determinant, U1, U2, V1, V2 times K. So this is an expression, I mean, these are the equivalent expressions for the cross product in terms of 2x2 determinants. Or if you don't like determinants, you can use this. And there's one formula that condenses all this, which is that the cross product of two vectors formally is a 3x3 determinant. If you write I, J, K, those vectors is the first row, U1, U2, U3, V1, V2, V3. This is formally like a 3x3 determinant. This is really U2, U3, V2, V3, that determinant times I, minus U1, U3, V1, V3, that determinant times J, plus U1, U2, V1, V2, that determinant times K. So that is the cross product. So just to make a couple of calculations, some examples. Suppose U is the vector 3, 5, 0. V is the vector 0, 3, minus 6. So U cross V, what is that going to be? So I, J, K, 3, 5, 0, 0, 3, minus 6. This is the determinant of 5 minus 6, 5, 0, 3 minus 6 I, minus 3, 0, 0, minus 6 J, plus 3, 5, 0, 3 K. This determinant is minus 30I, minus, this is minus 18, and this is 9. So we get minus 30I plus 18J plus 9K. That's the calculation. If we were to calculate V times U, so we have I, J, K. The second row is the coordinates of V, 0, 3, minus 6. The third row is the coordinates of U, 3, 5, 0. So this would be 3 minus 6, 5, 0 I, minus 0 minus 6, 3, 0 J, plus 0, 3, 3, 5 K. This is 0 minus 30 is plus 30I. This is minus 18, which is plus 18J. And this is 5 minus 9, minus 9K. And you'll notice this is exactly the negative of this vector, which is what it should be. V times U is minus U times V. Any questions about that? Now, there are several geometrical applications of the cross product. One is to compute the area of a triangle. So suppose we have the triangle with vertices 0, 0, 0, 2, 3, 4, and 3, 2, 0. So there is an effort to draw this in the text. So this blue triangle is the triangle I just described. One vertex is at the origin, 0, 0, 0. One vertex is the vector from the origin to the point 3, 2, 0 in the xy plane. And the third point up in space is the vector whose coordinates are 2, 3, 4. So this triangle in blue is the one we are interested in. And we want to find the area of that triangle. So let me just try and sketch this. Let me get back to the picture. So somehow we have the origin, we have this point, which is called Q, and then we have this point P up in space, P, whose coordinates are 2, 3, 4, and this is the triangle whose area we want to find here. I kind of sketched a proof out. And it is always the case that if you have a triangle, you can construct from it a parallelogram. And the area of the triangle is half the area of the parallelogram. And what can you say about the area of a parallelogram? Well, area of a parallelogram is the base times the height. So if this is, for example, the vector OQ, and this is the vector OP, what is the height? This height, called H, is the length of OP, the length of OQ. This angle is theta. This height is H over this. Sine of theta is H over OP. So the height is the length of OP times the sine of theta. So the base times the height is the length of the vector OQ times the height, which is the length of the vector OP, times the sine of theta. And this is exactly the cross product of the vectors OP times OQ, absolute value, the length of that. So the area of the parallelogram is the magnitude of the cross product of the two vectors that form its sides. And the area of the triangle is half the area of the parallelogram. So the area of the triangle is a half the length of OP times OQ, cross product. So how do we find the cross product? Well, the magnitude of the cross product, I, J, K, the vector P is 2, 3, 4. The vector Q is 3, 2, 0. So this is 3, 4, 2, 0, I minus 2, 0, 3 minus 2, 4, 3, 0, J plus 2, 3, 3, 2, K. So this is minus 8 I minus 12 plus 12J, 4 minus 9 minus 3, 4, 2, 0. That's minus 8I, 2, 4, 3, 0, minus 12, plus 12J, 4 minus 9, minus 5K. So that is the cross product vector. And the length of this vector is the square root of a squared plus 12 squared plus 5 squared, which is the square root of 64 plus 144 plus 25, which is the square root of 208, 233. And half of that, 1/2 the square root of 233, that is the area of the triangle. Right? Any questions about that?
Again, how do you ended up getting minus 8I plus 12J minus 5K?
Right.
Can you repeat that again? Sorry.
Yes. So I have two vectors whose coordinates are 2, 3, 4 and 3, 2, 0. Right? And I want to find their cross product. So a way to set up the cross product that's easy then to calculate. I mean, there are other ways to do it, but this is the simplest way and the way the book prefers, and I also recommend. You write down this 3 by 3 matrix. The first row are the unit vectors I, J, K. The second row, 2, 3, 4, that's the coordinates of one of the two vectors. The second vector, 3, 2, 0, that gives you the coordinates for the third row. And the definition of the 3 by 3 determinant, or the rule you have to remember, is this is I times a certain scalar. And the scalar comes from the 2 by 2 determinant from the other two columns. So I, and then you look at the second and third columns, 3, 4, 2, 0. And the rule for a 2 by 2 determinant is 3 times 0 minus 2 times 4, 3 minus 8. Sorry. 3, 4, 2, 0. 0 minus 8 is minus 8. For the second coordinate, the J coordinate, you take the other two columns, you get 2, 3, 4, 0. This determinant is 2 minus 12 is minus 12, minus 12 is plus 12. For the K coordinate, you take the other two columns, 2, 3, 3, 2, and this determinant is 4 minus 9 or minus 5, right? So that's where these numbers come from. So this is the cross product The length of this vector is the square root of 233. That gives you the area of the parallelogram that those two vectors determine. The triangle is half the parallelogram, so you divide by 2 or you multiply by a half, and that's how you get this number. Right?
Oh, okay. Thank
If you
you.
haven't seen 2 by 2 determinants, all you have to see is this. If you have A, B, C, D, that 2 by 2 matrix, the determinant is AD minus BC. That's all you have to remember. And you always have the book in front of you if you don't remember.
Okay, thank you.
Any other questions about this? Again, if you ever take physics and you study electricity and magnetism, there are many things that involve the cross product. So here's another application of the cross product. It's a geometrical problem. Find a vector orthogonal to the vectors u equal to minus I plus 6k and v equal to the vector 2i minus 5j minus 3k. So here we have two vectors in space, and I want to find a third vector that's perpendicular to both of them. So these two vectors determine a plane, and I want to find a vector perpendicular to that plane. Remember, orthogonal is a synonym for perpendicular. So orthogonal, perpendicular, and actually also the word normal, they're synonyms. And what we know is a vector perpendicular to two vectors is the cross product. So to find some vector perpendicular to u and v, we just have to compute the cross product of u and v. So if I write this as my 3 by 3 determinant, I, j, k, the coordinates of u are minus 1, 0, 6, right? This is the same as minus 1 times I, 0 times j, 6 times k. So the coordinates of u are minus 1, 0, 6. Coordinates of v are 2, minus 5, minus 3. So this is, in terms of its coordinates, something times I minus something times j plus something times k. This something times I is the 2 by 2 determinant 0, 6, minus 5, minus 3. The something times j is the 2 by 2 determinant minus 1, 6, 2 minus 3. The something times k is the 2 by 2 determinant minus 1, 0, 2 minus 5. When you do this calculation, you get 30i, 4 minus 12 is minus 8, minus 8 is 8, and 6, no, sorry, minus 1 times minus 5, plus 5k. Oops, sorry, 3 minus 12 is minus 9, and minus 9 is plus 9. So this is one vector orthogonal to or perpendicular to the vectors u and v that I started with. Okay. Any questions about this? All right. So this is lecture number 4, class number 4. And this is really starting vector calculus very slowly. In the first lecture, we talked about vectors in the two-dimensional plane. In the second lecture, we talked about vectors in the three-dimensional space, R3. Lecture 3 was about the dot product. Lecture 4 has been about the cross product, sometimes called the vector product. And on Wednesday, we're going to talk about section 5 of this chapter, which are equations for a line and a plane in space. So how do you describe lines? How do you describe planes? This is going to be fundamental to our study of vector calculus. Also, something which you might have seen in calculus, but we'll do again, which is how do you find the distance from a point to a line? Or how do you find the distance from a point to a plane? If you're given 3 points in space, how do you find the equation of the plane that goes through those 3 points? Right? If you have 3 points that are not collinear, there's one and only one plane that goes through them. How do we find the equation of the plane? Okay. So that is what we will talk about on Wednesday. And that's getting rather interesting. After that, we'll talk a little bit about more complicated surfaces in three-dimensional space, spheres, cylinders, and so on. And then finally, next week, we'll actually start to do vector calculus. We'll look at vector valued functions and understand them a little bit. Okay. Any questions about anything we've done? If not, then I guess we are done for the day, and this lecture will be posted very shortly on YouTube. I'm also going to have at least one office hour after Wednesday, probably on Friday. So if you have questions about anything that we have done this week or will have done this week, it's a chance to go online and talk to me about it. Okay. Any
right, thank you,
questions before
Professor.
we end? Yes, sir.
Thank you, Professor, for
Okay,
the
thank you.
lecture.
All right. Take care, all.
Thank you.